All right, greetings, scholars. I think this brings us to the last section that we will talk about in Chapter 6 on exponential and logarithmic functions. And we're going to be working on Section 6.4, graphs of logarithmic functions. Okay. So first we want to take a look at finding the domain of a logarithmic function. Given a logarithmic function, how to identify the domain. Set up an inequality showing the argument greater than 0. Solve for x. Write the domain in interval notation. Okay, let's see this in action. What's the domain of this? Let me see. So now the way I used to do it, or the way I do it, is so again, in general, we can't take the log of 0 or negative numbers. So in other words, this x plus 3 has to be strictly greater than 0. So then we subtract 3 on both sides. If we solve this inequality, x is strictly greater than negative 3. Oh, and that's not it. And then so if x is, we need to solve the inequality or write it in interval notation. So first I'd like to graph it on a number line. So say this is our negative 3. If x is strictly larger than negative 3, are we talking about the numbers to the left of negative 3 or the numbers to the right? Well, if the alligator's eating a bigger thing, our numbers are bigger. So we're talking about, how did that happen? We're talking about all the numbers to the right of negative 3. And because it can't be equal to negative 3, we use a parentheses, right? And then to write this in interval notation, the far left is negative 3. The far right is positive infinity. Infinity always gets a parentheses. And again, because we don't want to be equal to negative 3, that gets a parentheses as well. Yeah, so we're good. So what's the domain of this log? Again, we can't take the logs of 0 or negative numbers. So in other words, this 5 minus 2x has to be strictly larger than 0. Okay, let me see. I'm going to subtract 5 on both sides. So then here, notice we're going to, if we multiply or divide by a negative, right? So we're going to end up dividing by a negative, right? We got to watch out for this guy. So that means the inequality is going to flip, right? If we multiply or divide by a negative, the inequality flips. And x is strictly less than 5/2. Okay. And I don't know why I'm always trying to stop there. So if x is less than 5/2, so say our 5/2 is here, right? X is less than, so are we talking about the numbers to the left of 5/2 or the numbers to the right of 5/2? Well, if x is less than 5/2, we're talking about the numbers to the left. Right? So we're talking about the numbers in this direction, right? And because it can't be equal to 5/2, we put a parentheses. So then we convert this to interval notation. The far left of this graph is going to be negative infinity. And the far right is 5/2. And I think both of these get parentheses. Okay. So characteristics of the graph of the parent function log base b for any real number x and constant positive b and b not equal to 1, we can see the following characteristics of the graph of f of x equal to log base b of x. It's a one-to-one function. That means it passes the horizontal line test and it has an inverse. Every y corresponds to exactly 1x. It has a vertical asymptote of x equals 0, so that's the y-axis serves as a vertical asymptote. The domain is the open interval from 0 to infinity, right? The range are real, so negative infinity to infinity. It crosses the x-axis at 1, 0, so b comma 1, let me see. So the x-intercept is 1 comma 0, and you have a key point b comma 1, right? It doesn't cross the y-axis. If the base of the log is positive or greater than 1, then the log is increasing. If the base of the log b is between 0 and 1, the log is decreasing. Okay. So increasing is the left one, decreasing is the right one. But notice they both have the vertical asymptote. So figure 4 shows how changing the base can affect the graph. Observe the graphs compress vertically as the base increases. Recall that this function has base e, right? So base 2, and then 2.718, and then base 10, right? So as the base is increasing, the graph is kind of getting squished vertically. Okay. So given a logarithmic function of the form f of x equals log base b of x, how to graph the function? Draw and label the vertical asymptote, plot the x-intercept 1, 0, plot the key point b comma 1, draw a smooth curve through the points to state that the domain is 0 to infinity and the range is all reals, and the vertical asymptote. Okay. So graph this and state the domain, the range, and the asymptote. Okay. So the vertical asymptote should be the y-axis. Let me see, when x is 0, y is 1. Okay, I feel like an easier way to graph this is going to first rewrite the log as an exponential, right? So say we have y equals log base 5 of x. If I wanted to write this in exponential form, it's going to be the same as 5 to the power of y equals x. And then use this to plot to find your points, right? Let me move this over a little bit. So we can still do our x versus our f of x, right? But instead of choosing values of x, I'm going to choose values of y, right? Let me see. So we'll let y be negative 2, negative 1, 0, 1, and we'll go ahead and do 2, right? So when y is negative 2, what is that, 1 over 25? X is 1 over 25, so it's slightly positive, but it's really close to 0, essentially. When y is negative 1, we get 1 over 5, then we get 1, and then we get 5, and then we get 25. Okay. So say this is our positive x. Say this is our positive y. Let me see. So with the x's, let's go, let's see. 5, 10, 15, 20, 25, 30, right? With the y values, okay, 1, 2, 3, 4, 1, 2. So we went 5, 10, 15, 20, 25, 30, and these went 1, 2, 3, 4. These are negative here, right? So then if we plot these points, let's see, really close to 0, y is -2. So we do have a vertical asymptote. Okay. When we're really close to 0, y is -2. So we have a point right in there. And then 1/5 -1, we're still pretty much really close to 0. And then when x is 1, y is 0, so that's about here. And then when x is 5, y is 1, so that's about here. And then when x is 25, y is 2. So that's about here. All right? So we start really close. Oh, let's try that again. We start really close. Let me try it one more time. Really close to the y-axis. We pass through these points, and it kind of goes in that direction. All right? So again, I felt like for something like this, it's easiest to graph if you rewrite the log as an exponential, right? So we rewrote it as 5 to the, we took the base of the log, which was 5. We swung it to the other side of the equal sign. It became the base of our exponent. And so y equals log base 5 of x is the same as 5 to the power of y equals x. Then it was easy. To me, it's easier from that point. Choose values of y and find the corresponding x, right? And so, like, you know, you saw, then from there, I think it kind of flows, right? Okay, so this was us doing it by hand. I'll let you kind of read through that on your own, and you see we get the same image here. Okay, so transformations of log function. So with that first one, we add, usually that should be adding a positive on the inside of the log, sorry. To kind of do a quick recap, when we do inside manipulations for transformations, when we manipulate the inside of our function, that's going to cause a horizontal change, and it's typically the reverse of our intuition. When we do outside manipulations, that usually causes a vertical change, and it follows our intuition, all right? So for instance, with that first part, if we add a positive on the inside, the positive x is to the right, but it actually moves the graph to the left. Okay. And then if we subtract the positive on the inside, even though the negative x is to the left, it actually moves it to the right. When it comes to those inside manipulations with something like this, you can ask yourself, okay, what value of x makes that 0? Right? So if we add c, then negative c would make it 0. So then that's why it goes to the left. But you only have to do that when you're working inside the base function, because again, inside is the reverse of your intuition, generally speaking. All right. Okay. So for any constant c, I'll just kind of let you read through that. And I think I'm just going to do this one on my own. Right? So here we're asked to sketch the horizontal shift of this alongside its parent function, including the key points and asymptotes on the graph. State the domain and range in the asymptotes. Okay. I'm going to do something similar to like what we did a moment ago. Okay. So we're going to let g of x, be our parent function, where it's just log base 3 of x. Okay. And we're going to let f of x, which is given, be log base 3 of x minus 2. Okay. So what I'm going to do is rewrite the first one as an exponential. So my base of my log swings to the other side. We're going to have, I'm going to write it as 3 to the power of y equals x. I guess, can I fit it? Okay. So then if we graph our x versus our g of x there, we're going to choose several values of y. So we'll go -3, -2, -1, 0, 1, 2, and 3. Okay. So when y is -3, 1 over 27, and then what, 1 over 9, and then 1 over 3, and then 1, 3, 9, 27. Okay. So then when we want to graph x versus f of x, so if we're subtracting 2 inside the base function, that's going to affect our x values, all right? So that should move it to the right. So let me see. Are we subtracting 2? If we want to move the graph to the right by 2, so the value of x there, basically what we're going to do is add 2 to all the x values, right? So the y, it's only going to affect the x. So we're going to add 2 to all the x values, right? So we're going to say basically like this plus 2, this plus 2, all of these plus 2. Okay. So then, I don't know. I'm going to leave it as a mixed fraction. So we got 2 and 1 over 27, 2 and a ninth, 2 and a third, 3, 5, 11, and 29. And then the y values stay the same. This should be -3, -2, -1, 0, 1, 2, and 3. Okay. So x is okay. So say this is my positive y in this direction. Positive x. And here is my positive y. Okay. We'll do G in green. So we'll graph this in green. And we'll do this one in blue. Okay. Okay. So for the parent function, the vertical asymptote should be, the y-axis, right? Okay. We need to get to 30. We want to go by threes. Sure. We need 10. Let me see. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. Okay. This is the origin. We just need to get to 3. So let me see. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 is fine. 2, 3, 4, 5. These are negative. This is -3 here. 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. Okay. So then for the green, really close to 0, -3, so we're here. And then -2, so essentially the same thing. -1 is a third. And then 1, 0 is here. Over 3 and up 1. Over 9 and up 2. Then over 27 and up 3. So we start close to the y-axis, passing through these points. Okay. Now, I mean, honestly, we could just pick up this graph and move it over. I'm going to get a copy and do that, right? And we'll show that everything should match up. I want to copy and paste. Actually, it's already done now. Let me see. I think I can put it about there. I'm just trying to get rid of all the stuff I'm not using. Not bad. I think we got it. Okay. Style. This color. Yeah. Right. So if we moved it, so all it is for the second one, we should have moved it to the right by 2. Okay. Let's see. When x is 3, y is 0, we'll use that as a focal point. Okay, that should be it. About right there. All right. So 2, slightly to the right of 2, we're at -3, all right? Yeah, so I think we're good. When x is 3, y is 0. When x is 5, y is 1. When x is 11, yeah, I think we're good, right? So all we did was move it slightly to the right. But the trick here, again, we subtracted 2 on the inside. So when x, we had to basically do the reverse. We had to add 2 at each step for that to work out properly. Okay. Because if we subtracted 2 from each x, it's going to move everything the wrong way. We wanted to move to the right by 2 and not to the left by 2. So we had to add 2 to each of them. Okay. And we probably could have chosen a better window so that we can see the change a little bit better. But yeah. Okay, let's keep going. Sorry, it's like, I usually like to make these videos when I first wake up, and I did that today, but I guess I'm still waking up, so that's why I'm doing all the stretching. Plus, I'm a little bit excited, like just trying to wrap it up, because then we're done with all the new material, you know. Let's keep going. Uh-oh, do I need to exit out? Let me back out. This is slide 22. Okay. So graphing a vertical shift. So then this is going to follow our intuition. If we add a positive on the outside, it's going to move the graph up. If we subtract the positive outside our base function, it's going to move the graph down. Okay. Yeah, that's fine. So sketch the graph of this alongside the parent function, include key points and asymptotes, and state the domain range at, we forgot the domain and range of the previous one. Okay. So again, we're going to let g of x be our parent function, which is going to be just log base 3 of x. Now I wonder if we can just copy. We can honestly copy what we had before and just make some changes. Did they say the domain and range here? Okay. I'm just going to get a copy of this. Okay. Let me see. Log base 3. So G is fine. Now we're gonna make some changes here. So let me get rid of this. Let me undo. Get rid of this again. Okay. Let me see. Yeah, let me just get rid of all of this. Okay. I need to get rid of the blue from here. Okay. So now for f of x, the change, I guess I'll do the change in like purple, I guess. So f of x is what? Log base 3 of x minus 2. So what this is saying is that because the minus 2 is outside our parent function, it's going to affect the y values. So the x values should stay the same, but the y values are going to change, right? So however the y values are going to change, that follows our intuition. This is going to move the entire graph down by 2. So that's going to be equivalent to subtracting 2 from all the y values. Okay. So we're going to say this y value minus 2, minus 2, minus 2, minus 2, minus 2, minus 2, and minus 2. And everything else stays the same. Okay. So then I think I am just going to go ahead and copy and paste. So with those x values, we have these new y values. So those x values are now going to correspond to, we got this negative 5, negative 4, negative 3, negative 2, negative 1, 0, and 1, right? So it should be the same graph that's just been shifted. And we'll do this one in blue again. It should be the same graph but shifted down by 2. Okay. So all I'm going to do, I could plot all of those points, the x versus the y's. Again, it should be a duplicate of this graph that's been shifted down by 2. I'm going to just try the same little thing I did before, because I'm just trying to get the image, so I got to get rid of all this other stuff. So like this can go, all of that. Okay. Let's see. There it is. There we go. And then we want this. Wait. Okay, and style. Okay. All right. So we said that the new graph is going to be the same as the original graph, but we shifted down by 2. So let me see. X is 1. So x is 1 should be at negative 2. So it kind of goes off the page a little bit, but again, we just took the original and shifted it down by 2 units. Okay. So again, the x value stayed the same, but the y values went down by 2. Okay. That's interesting. I didn't even know that was going to happen. And you see it here. Okay. So with the vertical stretch, if we're multiplying the outside of our base function, remember outside manipulations cause a vertical change and they follow our intuition. So if we multiply the outside of our base function by a number larger than 1, it should cause it to stretch vertically. If we multiply the outside of our base function by a number between 0 and 1, it's going to compress vertically. It's going to shrink vertically. Okay. So sketch the graph of this alongside its parent function. Include key points. See, we got to start doing these at domain arranges. I totally keep skipping that part. Right. Okay. We'll do something similar to what we did before. So we'll let g be our base function. So we're going to look at the graph of x versus g of x. And then we're going to compare that to x versus f of x. Okay. Okay. So we're going to choose y values. We're going to have our -2, -1, 0, 1, and 2. Okay. So now, the original, let me see. So our g of x, we're going to let our g of x be log base 4 of x. If we rewrite this as an exponential, and I'm just going to write it as, I'm going to replace g with y. Or we can say, we'll say 4 to the power of g, right? 4 to the power of g equals x. So now we're choosing several values of g, finding the corresponding x. So for instance, when g is -2, that's going to be what? 1 over 16? And then 1 over 4, and then 1, and then 4, and then 16. Okay. So now we're multiplying a 2 on the outside of our base function. So outside manipulations, that's basically like we're going to double our y values. The x values are going to stay as they are, and the y values all double. Okay. So the x values stay and the y values double. I think I'm just going to copy and paste. So the x values stay, and now all the y values double, right? So we're seeing like this times 2, times 2, times 2, times 2, and times 2. So then we get -4, -2, 0, 2, and 4. Okay. Let's keep going. So let's see. So the y values go up to 4, x's go up to 16. Okay. So this is my positive x in this direction. Here's my positive y in this direction. My x's, I kind of want to go out to 20. Y, we just need to get to about 4. Let me see. We can go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, my y values 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. These went by 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This is a -2. This just went 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. We'll do G in green. And we'll do F in blue. Okay. So let's see, the first point slightly to the right is 0. We're at -2. So about here. And then -1. And then 1, 0 is here. And then over 4 up 1. Over 16 and up 2. We do have a vertical asymptote. Okay. And then when we draw a graph, we start close to the vertical asymptote and we just pass through our points and it tapers off to the side like that. Okay. So that's the graph of g of x, our parent function. And then, so we cause the vertical stretch. So the graph of our other function is going to get stretched vertically. So I'm going to graph that one manually. Slightly to the right of 0, y is -4. So we're here. And then we're at -2. Right, essentially about there. And then 1, 0. Okay. And then over 4 up 2. Over 16 and up 4. Okay. And you know, the y-axis serves as the vertical asymptote for both of these guys. And then it's a similar graph, just passing through those blue points. That's the graph of f of x. Okay, so essentially what we did, we stretched it vertically. Stretched it vertically by a factor of 2. Okay. Oh, let's do the domain and range. Okay. So if we focus on f, the domain, the very left to the very right is going to go from 0 to infinity. All right. It gets close to 0, but it doesn't reach it, so that's why we use parentheses. The range being the very bottom to the very top, -infinity to infinity. And the vertical asymptote is going to be y equals 0. Sorry, x equals 0, which is the y-axis. Okay. So sketch the graph of this and state the domain, range, and asymptote. So it looks like we have two manipulations going on here, right? So what we're going to do, we're going to start with the parent function. Now, if we can just kind of look at it, if we start on the inside and work our way out, or if we follow order of operations, right? So parentheses, so we'll do this part first. This is telling us that we're moving our entire graph left by 2, right? It's the reverse of our intuition. So we want to make sure the graph moves to the left by 2, and then this is going to stretch it vertically by a factor of 5, okay? So we'll start with our parent function, g of x. So we'll say x versus g of x. Let me see. The parent function is just going to be log of x, right? So like y or g equals the log of x, so 10 to the power of y. Okay. So I'm actually not going to do that many. I'm just going to go -1, 0, and 1, right? So if our base function is just the log of x, so then in exponential form, right, where the base swings to the other side, becomes the base on the other side, we're going to have 10 to the power of g equals x. Okay, so that's how I chose several values of g. I realized that if g were 2, we're talking about hundreds, and then if g were 3, we're talking about thousands. I didn't really want to go that far, so I just restricted it to -1 to 1. We'll find for those g values, and we'll find the corresponding x. So when g is -1, x is 1 over 10. Then we get a 1. And then when g is 1, x is 10. Right? If g were 2, it would go to 100. Right? Okay. So if we say g of x plus 2, right? So I'll just do this one in black because this is like an intermediate. So we have x, and then we want to consider g of x plus 2, right? So if we're adding 2 on the inside, that's going to affect our x values, and the y values should stay as they are, right? So we're going to leave our y values, and now we're going to subtract 2 from every x, right? So we're going to say this x value, let me see, we're going to say like -2, -2, and -2. Let me see, that's 20 over 10, so -19 over 10. I think I might just leave it. That's fine. So this x value is -19 over 10. This x value is what? -1, and then 8. Okay. And then lastly, if we want to say x versus f of x, we'll do this in blue. To go from the black to the blue, we have to multiply the outside by 5, right? 5 times that. So that's going to affect our y value. So the x value should stay the same, but the y value should all change. We're going to stretch vertically by a factor of 5. So we're going to say this times 5, times 5, and times 5. Okay. So then ultimately, it looks like we finish with, we got like a -19 over 10, -1 and 8. Then this is going to be what? -5, 0, and then 5. Sketch the graph of this. So we don't have to do the parent function. We just want the graph of the final, and these are some points that we can graph. And so basically, we just took the parent function, we moved it left 2, and stretched vertically by a factor of 5. Okay. So say this is my positive x in this direction. I'm going to move it slightly to the right some since we moved our graph left by 2. Let's see. Actually, we can keep it about, that's like a -2 almost. So about like there. Okay. So x is left. We need to get to we need to go from like -2 up to about 8 or 10. Let's see. So if we go 2, 4, 6, 8, 10, that's good. 2, 4, that's more than enough. Here's the origin. The y values, we just need to get to like 6. We go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So I think on the x value we went by 2, 2, 4, 6, 8, 10, 2, 4, 6. On the y we went by 1s, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. These are negative. These are negative. Okay. All right. So normally the vertical asymptote would be the y-axis. But since we moved it left by 2, now vertical asymptote is going to be at -2. Okay. So when x is -19/10 is slightly to the right of -2, the y value is -5. So we're like here. Here's our -5. When x is -1, y is 0. So that's halfway, which is about here. And then when x is 8, we're at 5. So over 8 and up 5 is about here. Okay. We start really close to the vertical asymptote. We pass through our points and kind of tapers over to the right. Let me see. When x is 0. Sorry. Okay, so we get an image like this though. I was just trying to check something without a calculator. It wasn't working out too simple. Let me see. So the domain, range, and asymptote. So the domain is the very left to the very right. The very left is going from where -2 to infinity. Okay, so the domain, it runs from -2 to infinity. Infinity gets a parentheses. -2 gets a parentheses, right? We get close to -2, but we don't actually reach it. The range is the very bottom to the very top, so that's a -infinity to infinity. And the vertical asymptote is going to be x equals -2. Mm-hmm. That's fine. Mm-hmm. Let's keep going. So then reflecting about the x-axis, so we're going to flip vertically. That means we should be multiplying the outside of our base function by a negative. So notice here, the negative is outside of our base function. So that's it's like our y values go from positive y to negative y, so it flips vertically. Flipping horizontally over the y-axis, we're going to multiply the inside by a negative, right? Inside manipulations cause a horizontal change. Okay. Okay, I'm just going to work these. Sketch a graph of this alongside the parent function. Include the key points, asymptote, state the domain, range, and asymptote. Okay. So we're going to let the parent function, our g. So we're going to look at the graphs of x versus g of x. And then we'll have x versus f of x. Okay. Let me see. So I think it's something similar from before. So let's do, let me see, we're going to have a -1, 0, and a 1 here. It looks like our g of x, our base function is going to be just the log of x. And then if we want to write this in exponential form, it's going to be what? 10 to the power of g equals x. Okay, so with those powers of g, with those values of g, the corresponding x, the first one is going to be what? 1 over 10. Then we have 1, and then we have 10. Okay. So then, in order to go from g to f, we're replacing x with negative x. All right, so f of x is going to be g of negative x, right? Again, all we did was replace x with negative x. And again, this is equal to f of x. Okay. So our y values stay the same, but it's like our x values go from positive to negative, right? So we're essentially making all of these x values negative. The y values should stay as they are, but the x's go from positive x to negative x, okay? So then that's going to give us -1 over 10, -1, -10, and then the y value stays, so that's going to be a -1, 0, and 1. Okay, and then we plot those. Okay. So the green, okay, was positive, and then the new was negative. I'm going to erase these purple negatives, or let me, I just wanted to be clear that we're multiplying by a -1 there. Let me see how I can do this. All right, I'm glad I'm at least using a different color so you know that there's been a change. I'm going to say times a -1. All right, so you know that we're multiplying by a -1 there. Okay. So say my positive x is in this direction. Positive y is in this direction. X's, so we're just gonna need to get to 10s, so we can go like 5, 10, 15. The y values, let me see. We'll say that's a half and that's 1. That's a half and that's 1. Okay. So on the x-axis we said we went 5, 10, 15. And then our 1 is there. Okay. So the original, I think they both have the same vertical asymptote, which is the y-axis. Okay. So when we're slightly to the right of the y-axis, y is or g is -1. So we're here. And then over 1 up 0 is about here. And then over 10 up 1 puts us here. So that graph. Like that. Can I flip it? I can rotate it, but I don't think I can flip it. So then when we're slightly to the left of 0, so we're here. And then negative 1, 0 is here. And then negative 10, 1 is here. This is the graph of f of x. This is the graph of g of x. All right, so we can see that it's flipped horizontally over the y-axis. Okay. So then the domain, the very left to the very right, is negative infinity up to 0. The range, the very bottom to the very top, is negative infinity up to infinity. And the equation of our vertical asymptote is going to be x equals 0, which is the y-axis. Okay, we're almost there. So given a log equation, use a graph. Here it is, finally. Is this it? Almost, not really. This is something else. Let's see it. So solve this graphically, round to the nearest, let me see. So press y equals, put the function in, graph to observe the graph window, proper view. Find the value of x, we compute the intersection, okay? So we're basically, to solve the equation, we're saying where do the graphs intersect, okay? So we have that equals that, round to the nearest 1,000, okay. Let me pull up my trusty dusty. Before I do this, let me get a copy of this guy, just for visibility's sake. We have 4 natural log of x plus 1 equals negative 2 times the natural log of x minus 1, okay? So what we're going to do is the left-hand side on one line, the right-hand side on another line, and then see where those two cross, and wherever they cross is going to be the solution. So we're going to go to y equals, we got this 4 times the natural log of x plus 1. We want to compare that to negative 2 times the natural log of x minus 1. I'm just going to hit zoom standard. It's going to go 10 in all directions, and we'll adjust it. We'll zoom out if we need to. So 6. So we got lucky here. Okay. So then we want to see where do these guys intersect. So I'm going to hit second trace to access calculate. And I want option number 5 for intersect. So my first curve, right? I'm just choosing a point on my first curve. And then the second curve, there it is. I'm just choosing a point on my second curve. I'm just going to choose that one. And then we want to get as close to the intersection as possible. About there is good. Then I hit enter. So the x value, so we get the x is approximately nearest 1700. So 3 decimal places, which is going to be a 9, 1.339. Okay, so we got approximately 1.339. 1.339 is correct. Okay. So say we have a log function with all these manipulations. Again, if you follow order of operations, PEMDAS, please excuse my dear Aunt Sally, that gives you a sense of the proper order. So, you know, if we add a positive on the inside, that's going to move it left that many units. If we subtract a positive, it moves it right. Right? We kind of talked about how each of these affects the graph. This is a, it's going to cause a horizontal change. It's going to cause a vertical change. Multiplying the outside by a number larger than 1 is going to cause a vertical stretch. A number between 0 and 1, vertical compression. Flips vertically, flips horizontally, right? And then you can kind of put them all together at the end. Okay. What's the vertical asymptote of this? So the vertical asymptote, the only thing that's going to affect it is if we move it side to side, which is this -4, right? I mean, this 4 here. So this is saying we're moving left by 4. So instead of x equals 0, the vertical asymptote should be x equals -4. Notice that -4 makes a 0 inside the parentheses. So that's kind of where we got that from. Is that it? That's all it asks. Okay. How many more? We're almost there. Find the equation from the graph. Find a possible equation of this common log. Okay. So let me see. If we have y equals, we had this a log base b of x plus c plus d. I think those are all of them. Find a possible equation of the common log graph. We did move it sideways, right? So we have a couple of points to consider, right? Looks like we have the origin, and we also have, when x is, we have the point -1, 1. Okay, so here we're asked to find a possible equation of the common log. So we're going to use this general form, y equals a log base b of x plus c plus d. And when I look at the graph, it looks like it passes through the points, through the origin and through -1, 1. All right. So we're going to work with those points. So now it looks like the vertical asymptote has been moved left by 2. All right. So then that would show up as what? X plus 2. All right. If we move the graph left by 2, so then we might consider y equals a log base b. What do we say? X plus 2 plus some common difference plus d. Okay. So now let's try when x is 0, the corresponding y is 2. Let me see. Do we have any other information? Let me see. So when x is 0, y is 0. So then we're going to have a log base b of what? 2 plus d equals 0. Let me see. We could subtract d and subtract d, divide by a. So log base b of 2 equals -d over a. So if we swing it to the other side, or we write it as an exponential, we'll have 2 equals b to the power of -d over a. Does this help us? Now we could let b be 2 and that power equal 1, right? Let me duplicate this slide. I just want to pick up where we left off from. Okay. So then, I mean, if we're using this, we can say that b is 2, and then we can say negative d over a equals 1, which is the power on the 2. So then, I don't know if that helps us at all. But from here, we're getting d equals negative a. Let me think. But maybe we can use that b equals 2. Now the other piece of information, what? It's jumping all over the place. Let me see. We're also given what? Negative 1 comma 1 is the point as well. So again, we started with y equals a log base b of x plus c plus d. Okay. Now let's try that. Let's let b be 2, right? So at this point we have y equals, now we'll figure out some kind of way to use this other part. We'll put a pin in a. Let me think. So we're still solving for a. We can say log base 2. We said what? X plus 2 plus d. So now we said what? When x was negative 1, y is 1. So then that's going to be, that's going to be a log of 1, right? Because if x is negative 1, log of 1, and then plus some d equals 1, okay? So now log of 1 should be 0. So then from there, we get that d equals 1. So then if d, I don't know why I did that in green. So then if d is 1, d equals what? So from here, why does it keep going green? Go green, right? From here, we get what? D equals a negative a. So then a equals negative 1. Okay. So again, if we're starting with y equals a log of 2, log base 2 of x plus 2, or plus d, right? Let's just plug in what we have. So at this point, we have y equals a negative log base 2 x plus 2 plus 1. Okay. Now, I think this might be a little different than what the text got, but we can check and see if at least our points work. Or we could look at the graph and see if we get the same image. I think I'm more inclined to look at the graph. Oh, I already had it. Okay. So I'm going to go to my y equals and clear out this other stuff. So now we got negative. Okay. So we hadn't officially talked about the change of base. So notice how we have a base 2 here. If we want to change the base from base 10 to base 2, the change of base formula, like log base 2 is the same as log base 10 divided by the log of 2. Right? So to capture that log base 2, we would just say the regular log divided by the log of 2. Right? So we're going to have negative log of x plus 2. Then we're going to say divided by the log of 2. That's the change of base formula. It just seems like it never officially popped up. And then we're going to say plus 1. And then we'll do a similar window to what they have. I guess let's just match their window. So the x minimum is negative 4. Yeah, I know you guys can't see it. Now what I could do, be nice if I can make the whole thing bigger. All right, let me enter this data and then I'll shift it back to where you can see it. So the x min is -4. We want to go up to 7. We can go in steps of 1. The y minimum is -3. We go up to 5 in steps of 1. So now if we look at the window, the graph, it should match. All right. Oh, that was my talk. I was like, why is that moving? All right. So I think the graphs match. We have a vertical asymptote at -2. All right. And then we can verify that our points work. And we're going to compare. I think the book may have written it a little bit different, but we can make the connection. Okay. So let me see. I'm going to go to variables, and I want to calculate. For instance, when x is -1, we should get 1. Okay. When x is 0, we should get 0. Okay. When x is 2, we should get -1. Okay, so that's about the best we can do, right? So this equation is correct. Now let's just compare it to the way the book did it. So they talked about the vertical asymptote first, so they went on and captured that. That moved the entire graph to the left by 2, all right? So you say +2 to do that. Now they use the points -1, 1, and 2, -1. Okay. So when they plugged the first point in, it gave them k immediately, which we kind of realized after a little bit later. So their points probably were a little bit easier to use. Okay. So now they got a equals this. Let me see. X + 2 + 1. So we need to make the correlation between their a and our a. Now we have a log base 2. So they have theirs in log base 10, right? So this should be the same as the log of x + 2 divided by the log of 2. So 1 over log 2. Let me see. Okay, so now the log of 4 is the same as the log of 2 squared. So that power of 2 can go in front of the log, and then you get 1 over the log of 2, which is what we have. Because the log of 2 is the same as regular log divided by the log of 2, right? So these are the same. Again, if I need to write that out to make the correlation between what they have and what we have, I can. I just use the change of base formula, right? Because again, log of 4 is the same as log of 2 squared. So when you take the log of a power, that power can go in front of the log. So then 2 divided by 2, they're gone, and we're going to be left with 1 over the log of 2. But dividing by the log of 2 is the same as log base 2, right? So these two are the same. Okay. I'm glad we took some time for that. The wind is picking up outside. I'm going to put a door stop in so the door doesn't swing open. Okay. And then they verified by checking a few values, right? We kind of did something similar. We chose several values of x and just compared to make sure that our points matched up. And all right. Is it possible to tell the domain and range and describe the end behavior of a function just by looking at the graph? I want to say yeah. It's provided it has like the proper window. Let me see. Yes, if we know the function is a general log function. For example, look at figure 16. It approaches x equals -3. Let me see. Oh, I guess we don't have that graph. Figure 16. That's 15. Yeah, it looks like we don't have that one. Okay. All right. Well, with that, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care. Peace.